林彦廷博士来给我们演讲。It's our honor to have Dr. Yenting Lin to join our seminar today. And Dr. Lin was a student here at physics department. And after obtaining his bachelor degree, he went on to University of Michigan to study with Dr. Charles Doran, a very famous physicist. And after obtaining his PhD last year, he joined Max Planck Institute in Dresden. And today he is going to talk about population dynamics. And I have to mention that Dr. Lin, although he is trained, he is by training a physicist, he is also very good at mathematical analysis. So today he's going to tell us about the connections between physics, biology, and mathematics. Let's welcome Dr. Lin.
Thank you, Professor Ken. So, as you can see, that today I'm going to talk about fluctuation-driven shifting selection regimes in population dynamics. And this is a work that I've done in University of Michigan. But right now I'm in, as Professor Chen has mentioned, right now I'm in at Max Planck Institute. This is a joint work with Professor Charlie Doran, as well as Dr. Hae-Jin Kim, who is right now at Michigan State University. And we thank our sponsors, University of Michigan and National Science Foundation. So here is my outline. I'm going to talk about the motivation of the study, as well as our objectives. Then I'm going to talk about the models that we developed. And of course, I'm going to talk about analysis, but considering the background of the audience, I may just rush through the mathematical analysis part and then just show you the results and the main idea of our analysis. And finally, I'm going to talk about the conclusion. So the motivation is more like an introduction in this particular part of mathematical biology, that it all went back to 18th century when Malthus talked about population. He said population, when unchecked, increases in a geometrical ratio. What does that mean? That means if we use a continuous variable n as a function of time t, then we can write down the ordinary differential equation, where the left-hand side is the per capita population growth rate. And then on the right-hand side, there are two terms, one of which is a constant birth rate and the other is a constant death rate. And we know how to solve this ODE, which is merely depends on the SIGN of the right-hand side. This population density n either exponentially grows, decrease, or remain constant. However, that is not actually what Malthus tried to say in his famous essay on population. What he's trying to say is, when it is not checked, increases in a geometrical ratio. However, the subsistence, that is the material that is supporting the population, increases only in an arithmetical ratio. And let me remind you that back in that age, there is no sophisticated math that we can use, and everything is written in language like this. But Malthus says these two unequal powers must be kept equal, which implies a strong and constantly operating check on population from the difficulty of getting resource. So after about 50 years, Verhulst proposed the famous logistic dynamics. The idea is actually to use a linear decreasing function to the right-hand side. Usually in mathematical biology, we call it the fitness. The fitness linearly decreases as the total population increases, and the logic behind that is if you have a higher population density, then it is more difficult for you to actually get some resource. Therefore, the overall population growth rate is going to be smaller. Here, I want to say this K usually is called the carrying capacity of the environment. What does that mean? That means when the population density n is equal to K, then the right-hand side is equal to 0, and the left-hand side is dn dt is equal to 0, means this population density is stable. And we actually know how to solve this equation. And after non-dimensionalize this equation, the dimensionless form of this dynamics is always like this. There's no free parameters inside the system. And depending on the initial condition of the system exponentially fast, the population density is going to converge to the carrying capacity, which is 1 here. And I believe everybody knows how to solve this analytically. And then after 1 century, a special kind of population dynamics called the competitive Volterra dynamics is proposed. The idea is right now is that we have 2 different kinds of species. One is denoted by X, the other is denoted by Y, and then the left-hand side is again the per capita growth rate. And to the right-hand side, there is a term, a functional, where species X and Y compete for the same resource. So you might think of 2 different kinds of animals who is consuming the same kind of resource. So if species X has a higher population, say X is larger, then it's going to also propose survival stress to the population Y here, because when X is large, this whole term here is going to be also going to be small. So that means that it's imposing environment survival stress to the other. And depending on how they compete, you can put in different numbers or different parameters, alpha, beta, gamma, and delta into the system. A very special kind of competitive Volterra dynamics is when we consider X and Y are indistinguishable. And when they're indistinguishable, then all these parameters can be scaled, and you'll see a symmetrical stress of X posing to Y as well as Y posing to X. Actually, this equation, this set of equations is very easy to solve. What we can do is just to add these 2 equations, and physically what that means is just, since you cannot distinguish X from Y, what you do is just, what you can do is just add them up and then consider the total population dynamics, and then it's again logistic dynamics, and then we know how to solve it. But such a symmetry will be broken when we consider spatial competitive local Volterra dynamics. I'll give you an example, a very minimal example of what I'm talking about. So let's consider 2 patches. Patch 1 is denoted by this circle here, and patch 2 here. And they have their carrying capacity. The patch 1 is K1 and patch 2 is K2. And now let's consider 2 different species living on these 2 patches. So right now we have some nonlinear demographic dynamics here and there. And the demographic dynamics of species X and Y are the same. Nevertheless, if we consider when species can move from patch 1 to patch 2 or from patch 2 to patch 1, what happens is that you have to add in more terms to account for the population, the change of population due to these dispersion. So let me write down all the equations here. That right now we see a symmetrical form of the demographic dynamics, which is nonlinear, which is here. And then right here we see something like the change of population due to dispersal. And this is a very simple form of dispersal called passive dispersal or random hopping. That means that the per capita dispersal rate is actually a constant. And here, for example, mu x, which is merely a parameter, and then mu x times x2 is going to be the flux of x entering to patch 1, and then mu x times x1 is the flux of x leaving patch 1. Notably, this mu x and mu y are the hopping rates of species species x and y. They do not necessarily to be the same. And from statistical physics, actually, these terms are actually just the chemical potential in traditional statistical physics sense. Okay, so since they do not, mu x does not necessarily to be equal to mu y, the symmetry can be broken, and between 1970s to 1990s, actually, mathematical biologists are thinking about this problem, that why is a species with a certain dispersal strategy or rate chosen by evolution? That is, why should I choose a specific mu x? Say mu x is equal to 1 or 2 or 1.5. Is the chosen mechanism or rate unique? Can I, for example, can the species choose, for example, like 1 mu x is equal to 1 and the other is equal to 2, and they have the same fitness? And how does the environment affect the chosen dispersal mechanism or rate? And these questions are actually answered in the ODE or PDE sense. That is, a deterministic dynamics shows quite surprising results that in both patchy-like system, which is like the system that I showed you, 2 circles, or a system with continuous space, that is more like a reaction diffusion system, as long as your environment is heterogeneous, that is, as long as your carrying capacity is not uniform, then you want to move as slow as possible. That is to say, if I'm a species living on the domain, and if the other species who's moving slower than I move, then the other species is going to exponentially grow and then take over the entire population, while my population is going to exponentially decrease. And eventually I'm going to go extinct. So these are proven theorems by, for example, Robert Hawes. Think about the system which is 2 patches, so you see N1, N2, and then what it reports is that the only evolutionary stable strategy in a temporally constant environment is epsilon is equal to 0. That is, the chemical potential is equal to 0. Moreover, Alan Hastings showed that regardless of the geometry of the system, that is, you can have many different patches, as long as they are connected together and as long as the resource is not distributed uniformly, it is always the case that the slower one can invade to faster species. Furthermore, just at the end of the last century, Jack Dockery actually proved that the same property is also true, is also valid in a reaction diffusion system like this, where we see here is the diffusive part, and then we see something like here is a nonlinear demographic demographic population dynamics here. He also considered the mutation, but what I'm trying to say is, as long as the mutation is equal to 0, that is, as long as there is no mutation, the phenotype with the smallest diffusion constant, that is the first, will be favored. That is to say, you want to move as slow as possible. Then it sort of raised the puzzle that then why should any species disperse right now? For example, if you look at the any established population density, things move, right? Like animals move, plants, they disperse their seeds, and so on. So mathematically, this model got to be wrong, and over the past few decades, mathematicians are actually trying to figure out why. Okay. So then I would like to talk about specifically what I have been working on as a stochastic spatial competitive aerodynamics in the context of dispersal problem. Of course, the biological system, in biological or ecological system, there exist multiple sources of stochasticity. Specifically, what I care about or what we are interested in is the demographic stochasticity. It's going to be intrinsic, that it is due to the intrinsic discreteness of the population. That is, the population, when we measure the population is either, it's always integer value. So it's never possible to actually write down the ODE, which is the evolution of a continuous variable. So this intrinsic discreteness of the population, along with the random birth and death process, would give you certain kind of fluctuating pattern of the population. So think about a scenario. Suppose I have a cluster of 100 bacteria, and then in the next step, it's very, very unlikely that one of which divides into two, and then one of which die, right? So what happens is that as a function of time, when time evolves, you always see some kind of 100, and sometimes it goes to 101, and then 102, and then goes down to 100, and goes. So you see this kind of fluctuating pattern. And this is going to be profound when the population scale is small. This is actually predicted by probability theory, because if you have a population scale goes to infinity, then in most of the cases, you would expect the dynamics will converge to the rate equation, that is the ODE or the PDE. So in the past 50 years, roughly 50 years or so, a numerical study showed that demographic stochasticity and spatial homogeneity actually encourages passive dispersion. What does that mean? That means, suppose your environment is actually more uniformly distributed, or suppose you have a smaller population density. Then if you write down individual-based model, and then you let the system evolve, then the one who hops faster or move in between the patches faster can actually win the competition. Specifically, I'm going to show you this study by David Kessler and Leonard Sander. What they do is to devise a individual-based model. So in their model, there are two different species. It's still called it X and Y. And they live on a one-dimensional chain denoted by X. And the environmental distribution, that is a carrying capacity as a function of time, is a sine function, sinusoidal function. And of course, so a species can live on this patch, say, when X is equal to 40. There can be species X and Y, and they can hop to the left-hand side or to the right-hand side, and then they just do their business, randomly hopping to the left or right. Nevertheless, their demographic dynamics is like logistic dynamics. And by varying the average of this environmental distribution, and also the variance of the environmental distribution, what they show is that if you plot in the parameter space the average versus the standard deviation, that is about the square root of the variance, then what they show is when the population scale is large, or when the variance of the environment is large, the slow species actually can, as the ODE system, actually wins the competition. But there is a phase transition where the fast species is going to win the competition when your parameter regime is in this region. So what does that mean? That means suppose your carrying capacity, the average carrying capacity, that's the population scale of the system, is small, when demographic stochasticity is profound, or when the standard deviation is small, that is when the environment is actually more uniformly distributed, then the fast species actually wins. And what is actually more interesting for physicists is actually the boundary of this regime. Look at the axes of this diagram. It's actually logarithm. So it's a log-log scale. So it's actually a power law distributed boundary. So they were actually reporting this, and they use a very heuristic argument, which turned out not to be true. And I'll show you what this, our work, is actually to explain why this boundary looks like this. So, great. So let me summarize the introduction part, is that over the past 40 years, actually mathematical biologists use this rationale to talk about demographic stochasticity. So what they said is that by lowering carrying capacity favors dispersal because it elevates the role of demographic stochasticity, and then generates the unused habitat when local population have gone extinct. So the logic behind that is when you lower the population scale, it's going to be more fluctuating. And then from time to time, some of the habitat is going to have lower population, but the environment actually can support more. So you want to move fast in the sense that you can actually run through the system and then find those habitats and then reciting those habitats and then just claim that as your territory. So that's their rationale. But I'm going to show you that this is actually not true in some of the cases. Okay, so our objective is actually to identify the dynamics of such a regime shift and to predict the outcome of a competition and identify the existence of evolutionary stable dispersal rate. I'm going to show you what that means later, and then to figure out how a evolutionary stable dispersal rate, suppose it exists, depends on the property of the system. Right. So now that I'm going to show you the models that we devised to study this problem. First, we devised a two-body problem where in the model, this minimal model, since we are considering a heterogeneous environment, there got to be two patches, at least two patches. So the model reduction tells us that let's consider only two patches, and then it's heterogeneous, so the carrying capacity here is not the same as the carrying capacity there. But there are two different species denoted by red and blue, and both red and blue, it's an individual-based model. They have the same identical demographic processes, that is a birth and death processes. Specifically, each individual in the system has asexual reproduction. So with rate beta, that means for each individual, after it waits for a exponentially distributed random time with this rate, it becomes two. It generates one offspring. And the death process of the system looks like this. So this is a rate of the system. Both of them gone through this rate. Notably, there are two different kinds of death rate. First kind is just a constant, delta. So this is characterizing the intrinsic death events of the system. And the second part here, which is proportional to total population on patch 1 divided by a population scale lambda times this delta, is the death events when they are competing for the resource, limited resource on this patch. So suppose x1 is actually higher, it's also going to increase the death rate of the death events of one. Okay. So the prefactor here is not the same from this patch to that patch. So that's only a prefactor. So this is the whole system, and it's going to be a very minimal system that we consider. So as a physicist, we propose another model, which is a mean field model, where again there are two different species, red and blue, and but once again in this system there are infinitely many patches. So that's a mean field approach in the sense that when one of an individual tries to hop to the other to another patch, what it does is actually just choose a random patch and then just hop onto it. And I forgot to mention that the carrying capacity of each patch is actually determined by some quench random number. Okay, so let me show you our analysis as well as the results. The outline of our analytical approach is actually to derive a master equation of a joint birth and death hopping process. And as usual, it is almost hopeless to actually solve the master equation directly. And in a large but finite population limit, what we do is to derive a Planck approximation by system size expansion, also known as the Van Kempen's expansion, and the corresponding stochastic differential equations. And the hope is actually to solve the Fokker-Planck equation and the boundary value problems, to actually characterize some of the features of the system. But it is, again, very difficult to solve it. Actually, we spent more than a year trying to solve this, and eventually we failed. So what we end up doing at the end is actually to use our physical intuition to develop something called a physically motivated asymptotic approximation. I'm going to talk about this later. Numerically, since it's a Markov process, we can actually develop simulation of the individual-based model, and it's straightforward. Yeah, everybody knows how to simulate each simple path and do statistical analysis. And I'm not going to talk about great detail about this continuous time Markov chain simulation. It's actually just a sort of Monte Carlo simulation, but philosophically it's not the same. We're actually simulating each simple path exactly and then do statistical measuring at the end. Okay, so I'm going to show you the results, some of the visualization of such a two-patch model. Let me remind you, in two-patch model, we have two different patch, different in the sense that they can support different amount of population, and we have two species, red and blue. That is said, our random variables is four-dimensional in the sense that we have a population of species X on patch 1, population of species on patch 2, species X on patch 2, as well as Y1 and Y2. In order to visualize this system to you, I project it onto a two-dimensional phase plane. And so I'm going to denote my x-axis as a population of X, and y-axis as a population of Y. And now I'm going to denote the information of the population on patch 1 as a red dot. So that means here is the population of species X on patch 1, and here is the population of species Y on patch 1. Similarly, I'm going to use blue to denote the population of patch 2. And the total population, let me remind you, which is equal to X plus Y, is going to be the diagonal axis. And when X plus Y is equal to K1 and K2, respectively, the carrying capacity of the system, then I'm going to draw a dotted green line here. And let's think about a scenario when both of the points is absorbed on this axis. That means the entire population of Y of the system is actually 0. So when you see these two dots being absorbed to the axes, that means some extinction event happens. And what we end up doing is actually to measure the probability of the extinction of Y or the extinction of X, as well as the mean extinction time. A technical point is that we define the population difference Z as X minus Y. So we are actually rotating the entire this phase space. Okay, let me show you. This is a traditional simple path when the population scale is around 200. And as you can see that the population is fluctuating a lot